This video is a preview of the definition of integral. The definition is quite long and I won't get to it yet. Rather, I'm only going to introduce the main ideas I will need, and in a later video, link in the description, I will formalize these ideas into the actual definition. I'll begin with a geometric interpretation. Let's look at the function f. For now, for simplicity, I will assume it is positive and continuous. I take an interval ab in the domain of the function, and I look at the region that I am shading in this picture between the graph of f and the x-axis. I could like to define the area of this shaded region to be the integral. There are a lot of new symbols here, so let's look at them closely. This whole expression is new notation. We read it as the integral from a to b of f of x with respect to x, where f is a function and a and b are real numbers. For now, the last part, the x, is just a piece of notation to indicate that the variable is x. We will later give it more meaning. Sometimes this whole phrase is abbreviated simply as the integral from a to b of f. We will call this a definite integral. It is a number. Which number? The area of the shaded region in this picture. Notice that this is not a formal definition, because I do not know what the area of an arbitrary region is. In general, I only know how to compute the area of very simple regions like rectangles or triangles. Instead of as a definition, I will take this as motivation of what I want an integral to represent. I will spend some time trying to come up with a method to calculate the area of an arbitrary region, and once I have that method, I will use that calculation as the definition of integral. There are three key steps in this construction. First, I am going to stick with the simplest shape whose area I know, the rectangle. I can try to estimate the area of this region with rectangles. I am drawing a rectangle that is contained in the shaded region. It is red in the picture. The height of the rectangle is the minimum of the function on this interval. I'm calling it little m. The red rectangle gives me an underestimate of the area I want to compute. The integral should be greater than or equal to little m times b minus a. Similarly, I can draw a rectangle that contains the shaded region. It is in green in this picture. The height of this rectangle is the maximum of the function on the interval. I am calling it big M. The green rectangle gives me an overestimate of the area I want to compute. The integral should be less than or equal to big M times b minus a. These two estimations are very rough. Unless my function is kind of flat, they won't give me an accurate value for the area at all. But they are a start. Here's the second idea. I can improve this estimation if I first cut the region into vertical slices. For example, in this picture, I cut the region into 4 slices, and now I can estimate the area of each slice with a rectangle separately. I can underestimate with red rectangles below, and I can overestimate with green rectangles above. These estimations are still approximations, they are not exact, but I see they are a better approximation, the error is smaller. How can I get an even better approximation? What if instead of 4 slices I use more, and more, and more? Now I see it. If I take a lot of slices and make them very thin, this estimation looks pretty good. That will be the third step. We now have a plan. First, I cut the region into slices. Second, I underestimate and overestimate the area of each slice with a rectangle. And third, I'm not sure what the third step is yet, but it involves something like taking many slices and making them very thin. However, we are not ready for the formal definition yet. Before I develop these ideas, I want to introduce 2 tools that will make everything easier. First, when I use many slices and I approximate each one with a rectangle, I will need to compute the sum of the areas of those rectangles. There is a notation, the so-called sigma notation, that makes writing long, complicated sums easier. I want to explain that notation. Second, in this video I have been casual and I have used the maximum and the minimum of the function for the heights of the green and red rectangles. However, there are lots of nice functions that do not have maxima or minima, and I want to compute their integrals as well. There are 2 concepts similar to maximum and minimum but more versatile, supremum and infimum. I want to explain what they are, and I want to use them instead. Thus, I am going to take a break and the definition of integral will have to wait. In the next videos, I will introduce sigma notation for sums and supremum and infimum. Once I have those tools, I will come back and try to convert the 3 steps above into a rigorous definition of integral. See you in the next video.